Good morning, everyone. I guess we get to enjoy a little bit of cool weather. And then, of course, as we get to the end of the week, I know the weather's changing because my nose starts to itch again. That's one thing about this good old Texas weather. I hope everybody's doing well and staying healthy. Remember, at this time of the year, it's good to drink plenty of water and try to rest as much as you can just to keep your mind focused because anxiety can get high and I always keep that in mind when I give you the extra time to the larger window to take your test. I know a lot of times you have a very small window to take a test, and I don't believe that you can perform well when you're stressed with time constraints. So I've tried to do that all term, and it's certainly going to be no different for the final exam. So, so as I mentioned, we will not have class, of course, on Thursday because you'll be taking your exam and probably taking care of other things. So today will be our last virtual lecture. I will have my office hours today and also tomorrow, and certainly I'll send out the emails for those to keep you aware of those if you need to take advantage of it. And another thing too, today what I want to do is go through the practice test that I put up on Blackboard. You can see it in the practice test as just a PDF with some solutions that I added, and also you can see it on the SmartPen videos. My students that don't work online or have the online on the schedule use those, but again, just trying to give you different ways to access material. So what we want to do first is just work through this. And then as we get towards the end, I want to say a little bit about the rotation of axes. It's kind of hard to fit in that topic, but I just want to give you a little introduction to it. And if you find it interesting, you may want to investigate it further. It's a nice topic, and it also can be introduced in a linear algebra class where you have the use of linear transformations, which actually make the theory a little bit easier. But, you know, just like we saw with the translation equations, you have what you call rotation equations that affect the rotation to get a new set of axes. Like we translate to get new sets of axes, we can rotate. But of course, with the rotation, we introduce the sines and cosines. And so that's a little bit more difficult. So let me go ahead and share my screen so we can go through this practice test. Now here, what I want to do is just basically go through the notes that I have written up for this to make the process a little bit more streamlined and to give you an opportunity just to refresh yourself on these ideas. And what you'll find with the final exam, ladies and gentlemen, there will just be a consistent coverage throughout the semester. There's not going to be a whole lot of new material. There's not going to be a whole lot of anything except just the basic survey coverage of the class. And a student earlier asked, well, how many questions? And I don't think that's usually very important. They're probably anywhere from like 25 to 26 questions and a little bit longer, maybe just a little bit longer than a regular test, but a coverage that, again, you're not going to have 2 or 3 problems on a particular topic. It's just going to be basically a coverage that gives you the survey of what we've done. And so as you study, you can focus on the new material to get that comfortable, and then go back and spot check some of the old. So hopefully by going through some of these examples, that'll give you an idea of exactly where you might need to do just a little bit of review. But I think most of you, you know your college algebra, and you've been hard workers with the new material. So I think you'll be in good shape. So let's look at the first set of problems here. The first one we have, and let me make sure my light is on. There we go. We have a function, h of x, which is equal to x minus 1 divided by x cubed minus 81x, and we're asked to compute the domain. Now, of course, this is a fairly straightforward problem. Namely, when we look at domains of functions, we're interested in making sure that the real input gives a real output. So when we look at this, we don't have any radicals, but we do notice the fact that division by 0 would be possible. At least checking this out, we certainly know we couldn't let x equal 0. But if we factor the denominator, we expose a difference of squares when we factor the x, and that gives us an x times an x minus 9 times an x plus a 9, which must be non-zero for this to actually have a well-defined real output. And so therefore, by zero product, it would be the case that x could not equal the 0, the 9, or the negative 9. So of course, in the answer selections, you have it written set theoretically, which is fine, but oftentimes in WebAssign, WebAssign will suggest please write with the interval notation. So of course, you know that could be written as negative infinity to negative 9, union negative 9 to 0, union 0 to 9, and then of course 9 to infinity with all open parentheses, so to speak, to exclude the negative 9, exclude the 0, and exclude the 9. So again, very straightforward. And again, like I say, as you look through the test and as you go through the test, you'll see that several concepts will be covered in one problem. Like, for instance, transformations, that might just be a one trig graph. You know, that would cover all the transformation problems, which you've had many of on your test, but I only have room for one because, you know, a final exam that's comprehensive basically has to be done in a finite amount of time. So we can't have an infinite test, so to speak. Now, the next problem, again, when you get to the calculus, you will be interested in the difference quotient, the change of f over the change in x, the independent variable. Sometimes this is written as like a delta y divided by a delta x. And so when you see something like that, you're maybe reminded of rates of change. And when you actually define the derivative in calculus, you will actually take a limit of this difference quotient. So this will be something that you will see often in calculus, and you will already have the algebra understood, which will make the process of teaching the calculus a lot easier. So in this case, we want to look at the difference quotient, ladies and gentlemen, where the actual function is 1 divided by 9x. So this is a rational function here. So what we can do, again, notice we need to write f of x plus h. F of x is just what it is, but notice we're dividing by h. So to clean up the algebra a little bit, it might be a little bit simpler just to write 1 over h here to the left to kind of move it out of the way of the algebra that we'll have to do here. Now, of course, this is just a transformation. Of course, in this case, we're not assuming that h is positive here. It could be anything non-zero. So in this particular case, we replace x with x plus h. So that gives us a 1 divided by 9x plus 9h. And then we subtract f of x, which is just the function. Now at this point, you're thinking this is an equivalent expression, and it certainly is a difference quotient, but what we want to do in the calculus is be able to allow h to pass to 0. That is, what we're trying to show is that the numerator converges to 0 quicker than the h does. And if it does, then the actual limit will exist. So what we do in order to show that is we first try to get a common denominator here. So we have the 9x plus 9h here, and we have also the factor 9x. And when we multiply these two, we need to get the concomitant change in the numerators. So here we have to multiply the 1 by the 9x, and here we have to multiply the negative 1 by the 9x and the 9h. And so that'll give us a 9x minus a 9x minus a 9h. So notice the 9x is absorbed. And then what are we left with? Well, we have a negative 9h divided by 9x times 9x plus 9h, and then times 1 over h. So now we can see the h is absorbed, And of course, the 9's absorbed, and we're left with the -1 divided by x times 9x plus 9h. And so now you might be thinking, well, this is suitable. This is good. We've gotten rid of the h. And so now h can pass to 0, and we're just left with -1 over 9x squared. But if you like, you can go ahead and factor the 9. And that, of course, would be your choice. But what I want you to see here is that the algebra is what really exposes the fact that this derivative does exist in this particular case, as long as we avoid 0, of course. I mean, we would never think of trying to create a tangent line at 0 because it's not in the domain. But certainly for any x non-zero, this limit would actually exist. So this is what you're going to investigate quite heavily when you take Calculus 1. Now, the next problem, again, a personal favorite. We noticed when we actually did our work with trigonometric functions is that of the 6 trigonometric functions, 2 were even and 4 were odd. So going back to this probably seems a little bit boring because it's not a trig function. So in this particular case, we have f of x equal to the negative of x cubed divided by 6x squared plus 4. And so what we want to do is, based upon the directions here, is check whether or not even or possibly odd or neither. So remember, when we do these kinds of problems, the first thing that we want to do is check for the domain, because remember, the domain must be symmetric relative to the origin. So one thing that's easy about this is that the 6x squared plus 4 is never 0. This will never give us a 0 output for any x. So we get the domain is just all real numbers. And of course, relative to the origin, the real number line is symmetric. Remember, it's like if we didn't have a 2 in the domain, we'd also have to lose the -2. That way, if x is in the domain, then its additive inverse is in the domain. That's how we get the symmetry. And that's very important in the definition. So we see we have this. Now the next thing we need to check is, how does f react to the additive inverse? That is, if we replace x with its negative, what do we get? That is, how does this impact the function? Well, this is a simple process, and of course we love our trig functions because it's built into the unit circle. But here we just simply replace the x with its negative. Now, of course, with the sequences, this has become old hat. If we cube the -1, the negative survives, and then we just have a negative of x cubed, which we have here. Now, of course, the negative's still here, and then we have noticed that the negative x here, when we square it, absorbs. So we just get a 6x squared plus 4. Now, of course, if we went from here to here, you would say that the negatives absorb, but you really don't need this, but I kind of did this just to make a point. You might get here and say, well, I don't know, Professor Ron, I think it's neither. But here's the deal. These are equivalent. So if I take this one and rewrite it, I can write it this way, but I can also rewrite it with the negative factor. That is, take one of the negatives and push it to the left, and we basically get the additive inverse of the original function here. That is, what's in the brackets is the original function. So oftentimes when you've got the 2 negatives, you're probably better off bypassing this part and just going directly to here with the brackets. And then you see that f of negative x is just the negative of f of x. And that defines the odd function. So by definition, f of x is an odd function. So again, I don't think this is anything that gets rusty for you. We spend so much time with even and odd, but just maybe when we talk about the algebraic functions, it's good just to go back and review and just remind yourself that we always have that symmetric domain when we talk about even and odd functions. I mean, it's the linchpin of how things work because of the additive inverse. We need the additive inverse in the domain. I mean, like if 2's in the domain and -2 isn't, how can we ever, check that property? So we need the symmetric domain. Okay, now number 4, again, a very simple problem, and you're thinking good old quadratic functions, those are just parabolas. And so why do we have to rock the boat and talk about conic sections? And I'll agree with you, it just adds more stuff to have to contemplate. But it's nice to think about a curve as a parabola when we think of the properties of the conic section. And of course, when you think of parametric equations that you're going to talk about in Cal 2 and Cal 3. So it's one of those necessary things. So when we look at this problem, we think back to the first week of pre-cal when we reviewed college algebra. A farmer has 1,000 yards of fencing to enclose a rectangular garden. It says express the area A of the rectangle as a function of the width X of the rectangle. And then it says, what is the domain? Well, you know this is going to create a quadratic function, and it's actually pretty simple. So what I did here is, again, I just used the directions to assign the width to be X. And then, of course, that gives us a letter for the length, which we can just set as Y, your choice. You could call it L if you wanted. And then we've got 1,000 yards of fencing. So that would be equal to the actual perimeter. That is 2x times 2y. And the directions say to write a function of the area in terms of x. So what we can do is basically, if you like, you could just divide through by 2, or you could subtract 2x from 1,000 and then divide by 2 like I've done here. Either way is fine. And then, of course, when you distribute the 1/2, you'll get a 500 minus x. Now, this gives or opens the door to a technique I taught you about with quadratic functions, especially when you don't have a constant term. Notice now, if we define the area A of x, that means we take the width x and multiply it by the actual length, which is 500 minus x. And there's the area right there. Now, of course, this is where I would tell you, ladies and gentlemen, if you have a situation where you've got 2x intercepts, that you can basically read from the equation in the factor form, then the midpoint gives you the actual vertex. So notice we have a 0 at 0 and a 0 at 500. And so, of course, the h or the x coordinate of the vertex would occur at 250. And of course, since this is going to have a negative, when we multiply, this will have a maximum. So if you were asked to find the maximum of this function, you could just simply evaluate a at 250. But if it's written this way, that would just be 250 times 250, which is very simple. And then, of course, that'll give you a 625 with 2 zeros. So again, there is a lot of utility that we can gain from writing quadratic functions in factor form when we have the lack of a constant term. So of course, to finish the problem, you could just simply write the area as negative x squared plus 500x. And then, of course, note that you get 0 area at 0 and 0 area at 500. So that kind of gives you a envelope between 0 and 500 where the function would have a defined area. I always include zeros, especially when I do optimization problems in calculus, because those define clear delineations between a volume or an area that makes no sense and no volume or no area. I mean, no area is certainly possible. I mean, you know, it's one of those extreme cases, but you do need to consider it so that you can set up your problems correctly. So we could certainly have an answer that looks like this, and that would correspond to A. Now, again, very simple, just good to get back into the old way of doing college algebra. Now you look back and say, well, you know, I'm pretty good at this. It's not so bad after all. So let's look at number 6. I thought this was an interesting problem because there are a couple of examples with transformations here. Just to, again, remind you of basically what transformations do and to remind you of how to actually execute them. So this one is not an unraveling problem. Remember the times when we get a function and we have to figure out the graph by unraveling it? That's usually a little bit harder, but that's what we had to do with the trig functions. Exactly that. So let's take the reverse problem. Let's start with the square root of x, and let's do an upward b shift by 2, followed by a reflection in the y-axis, and then followed by a right shift by 8 units. And they say finally graphed. It's like, you know, like the end of the world. I guess these were not English majors, but neither are we. So I should not criticize. So when we look at this, oh, and I skip, since I skipped 5, I'll come back and get it since I already talked about 6. Sorry about that. I'll come back and do 5. You're thinking, Professor Ron, you skipped 5. I'll come right back to it. So let's go ahead and do this. So we have square root of x, and let me touch up on the focus. Let IPVO do its work. Okay, so we do an upward b shift by 2. So we simply add 2 to the square root of x. And then we affect the y-axis reflection. So that means we must replace x with its additive inverse. So we get the negative of the square root of x plus 2. So that definitely changes the domain and shoots it off to the left. And then we do a right shift by 8. So again, that means, at least algebraically, that we replace x with x minus 8. So here we have the negative of the quantity x minus 8 plus 2. And then, of course, we just distribute the negative, and we get negative x plus 8 square root plus 2. So that's a simple problem, but it's a good problem that requires you to distribute. We often, you know, we'll do a reflection or something of that nature, and we'll just apply it to one term, and that's not correct. When you have a negative, you must apply it to all terms. If you've got a sum and, you know, an addition of 2 terms, the negative must be distributed. And that's a real simple mistake to make, but we don't want to make that. Now, what about the problem I just left out? Okay, well, here's another transformation. It says, suppose that you have a function f of x that is decreasing on a given interval 5 to 7. Okay, then it says, what about the negative of that function? What is it going to do? That means if you reflect it in the x-axis, what's going to happen to that function? Well, intuitively, I think you know, but let me just go ahead and show you how we can do this just using the definition. Now, again, it really wouldn't matter when you're doing a test as long as you get to the right answer using good math. I mean, how you do it is immaterial. So, for instance, if f is decreasing, what we can do is write formally. That is, let's take an x1 and x2 in the interval 5 to 7. And if we assume that x1 is less than x2, then a decreasing function would have values that would get smaller as we progress through the interval. So it would be the case that f of x1 would be greater than f of x2 because the values would have to be dropping as you move from left to right in the interval 5 to 7. And so then you're thinking, well, if we reflect it, it's going to increase. Well, why is that? Well, it's easy. If we multiply this inequality by -1, of course, we reverse the inequality, and then we get the negatives. We get the negative function. We get negative f. And so now you can see if x1 is less than x2, then the negative of f of x1 will be less than the negative of f of x2, which means that the function is by definition increasing. So you can look at a picture, or you can just apply the definition. And then, of course, we know that multiplication of an inequality, a real inequality, by a negative number or a number less than 0 reverses the inequality. So we're basically using many of the very nice properties of the real number system. The real numbers are important because not only are they a field with all those nice operations, but they're complete. The real numbers have no holes. When you draw the real line, that's the best way we can basically symbolize the fact that real numbers are complete. You don't walk along the real number line and hit a black hole or hit a pothole. The real numbers form a complete ordered system. So that's why we like to do calculus with the real numbers. It's a very useful set for calculus. Okay, well, sorry about skipping that. It does happen. Now, so let's look at the next one. Back to the quadratic functions. Again, when you study the quadratic functions, you pretty much study the parabolas, but we did, spend quite a bit of time on this in section 1, chapter 3. And of course, this helped ease the transition into parabolas once you figured out that the directrix was part of the scheme also. Only if you define the parabola in terms of the focus and the directrix. So when we define the quadratic function initially, we don't really refer to a focus or directrix because we're not looking at it as a conic section. But how interesting that the two curves coincide. Now, what this says is to define or to determine a quadratic function that has these 2 points. That is a vertex of 2, -2, and then a point of 0, 2. So that's a unique function. Again, when we think about the fact that we're given the vertex is a distinguished point. And what makes this work is that we have this nice completed square form right here. This completed square form tells us if we have the vertex HK, all we need is an additional point to determine the coefficient A. We're not looking for a P like the quadratic or the parabola. We need the A. And so now we can simply replace the H with 2 and the K with -2 to give us A times X minus 2 quantity squared minus 2. And now we just take the point 0, 2 to solve for A. So in this case, we'll have 0 is equal to, in this particular case, 2 is equal to this term here, but then we can transpose the 2, that will give us a 4, and we're left with A times 0 minus 2 squared. So we're just left with -2 squared. But of course, the -2 squared is 4, and if we divide 4 by 4, we just get 1. So, and of course, what we see here, this is A times 1 equals 1, so to speak. So once we have the A, then we can just fill it in. That is, now we have f of x is 1 times x minus 2 quantity squared minus 2, and we can expand it. You're thinking this is fine, WebAssign would like this, but if we're looking for an answer in a list, we want to make sure that this is equivalent to that list answer. And so we can expand it using the binomial theorem. That is x squared minus 2ab plus b squared. So we get the x squared minus 4x plus 4 minus the 2, which gives us x squared minus 4x plus 2. So that is the unique quadratic function with these attributes here. So again, you've done several of these types of problems with hyperbolas and ellipses, where they give you certain parameters like vertices and foci, and you determine the equation of the ellipse, because for a hyperbola, you know that c squared equals a squared plus b squared, and for the ellipse, c squared is equal to a squared minus b squared. So you have all these nice conventions that allow you to produce the unique conic from given information. So this is very similar to that. Now, let's look at the next problem. Notice in this particular case, we have solved the inequality, and of course this will be in the real numbers. We have 25x squared plus 9 less than 30x. Okay, now if you looked at the SmartPen videos, this is kind of an interesting problem. Notice the first thing that we want to do is to utilize zero product. So we retire everything to one side and get 25x squared minus 30x plus 9. But of course, even if you don't recognize this as a perfect square, the AC method will uncover it. Because of course, this will give us a 25 times a 9, which is 5 squared times 3 squared. But that's just 15 times 15. That's the perfect square. And so with that, we know that this is just an A minus B quantity squared. So we can easily uncover that. This is just 5x quantity squared. This is 3 squared. And of course, this is the minus 2AB right here. And so this just gives us the quantity 5x minus 3 squared less than 2, excuse me, less than 0. Well, a non-negative quantity cannot be less than 0 by definition. So as I've written here, this is never true. So that there would be no solution, or the solution is no solution. So just remember that you don't usually expect things not to work. Like when you're asked to solve an equation, you usually or tacitly assume that there's a solution. Well, there doesn't have to be. And then of course, if you get no solution, you tend to think you need to recheck your work. But in this particular case, we have no solution. Now, let's look at number 9. Now look at 9 and think about what we've done with rational functions. When it comes to rational functions, ladies and gentlemen, we usually like to start out pretty simple, or we want to put it in a form where we can determine asymptotes, where we can determine intercepts, and that way, and maybe some symmetry or whatever. But usually, if we get enough information from the first 4 guys, or at least the asymptotes and the intercepts, then we're thinking we probably have enough information along with maybe a simple sign test to get a reasonable graph. So we have f of x equal x plus 9 over x. So first off, we can look at this and make a few comments. That is, clearly x equals 0 will give us a vertical asymptote. But if you look at this, the way it's set up, here is the infinite part that identifies the asymptote, and this is the part that's kind of off to the side. That is, as x gets large, this decays to 0 negatively and positively, going off to negative infinity and positive infinity. And the dominant term of the function becomes the x, just like we have with horizontal asymptotes. So we have a slant asymptote here of y equal x. Now notice if we just think about a common denominator here, because you're thinking this can never have a y-intercept because x equals 0 is undefined. And then you're thinking this can never be 0 because this is equivalent to x squared plus 9 divided by x. And that can never be 0 since x squared plus 9 is always positive for any x. So when we look here, we see no x-intercepts, we see no y-intercept, and we've got the vertical asymptote. But now here's another thing that you may have already noticed. We have this nice symmetric domain. It just excludes the origin. And of course, this is an odd function. If you replace x with its negative, you just get the negative of the original function because these are just x's to the first power. So that negative factor. So this is clearly odd, but you don't really need that. All we need to do at this point is just kind of figure out the sign test, which again is kind of obvious. If we take x negative, the overall sign will be negative. If we take x positive, the overall sign will be positive. And so we know using the sign convention that we have to approach positive infinity as x approaches 0 from the right and negative infinity. But clearly, this must now approach the slant asymptote and of course never descend to the x-axis and cross the asymptote just because there are no driveways down here. So when we look at this, we're thinking, wow, this is a simple function to graph if we appeal to what we know about rational functions. And then of course you can think about the trig functions like tangent and cotangent that have really freaky graphs with all these, you know, they're blowing up to infinity, but they even cross through the origin. So this is kind of a broken record, so to speak. We see this occurring a lot. But what I've written here, and this is something I talked about before, with the pre-calculus methods, we could try to estimate here what we think this relative max is and this relative min, but we will need the concept of derivative and some of the maximizing properties that we get with the first derivative to figure out the point here where we have a local max or local min here. So sometimes the phrase is relative max. You also say local max. You can then say relative min or local min. They are interchangeable phrases. Dr. Larson tends to use the relative term. Other authors will use local, but they mean the same. So the idea here is that you know this is a relative max because the function can get much larger than this value here, but locally it is a maximum. Locally there's a minimum value here, but we cannot discern that using the pre-calculus techniques. We do need the calculus. Okay, so that's an interesting problem. Now, for the next example, I made sure with the practice that we had plenty of basic technique practice, just so that you don't forget BVs, just so you don't forget asymptotes, just so you don't forget what a logarithm is, just basic fundamental topics that keep your mind moving, so to speak. Now, for this next problem, it says solve the inequality. And then we're thinking, well, wouldn't it be nice if every inequality came in this packaging? We have x minus 7 divided by x plus 9 is less than 0. But here's the thing. If you understand the technique, then you can look at this and say, well, we already have the 0, and we've got very simple factors here. So we didn't have to do any elaborate algebra to create the 0, and we already have the factored form, so to speak. So we can see that this expression here is 0 at 7, and it's undefined at -9. And that's where we have to investigate. That is, what happens in the regions that are created by these boundary values. And so we just mark off the boundary value 7 and -9, and then we can just take test points. So if we try 0 here, of course, in this case, we'll get a negative answer. So we have a negative sign here. And then, of course, on either end, if we try the 10, again, we get 2 positives, and the -10, we just get 2 negatives, which again results in a positive. Now, in order to solve this, we simply go to the region where we have negative values. That is, the sign of this is actually less than 0, and we see that's right here. So again, sometimes problems are just a matter of exercising the techniques that we've developed. Algebra is just a part of doing mathematics. We're doing conic sections. You might have to do a lot of arithmetic. When you're working with geometric series or arithmetic series, lots of arithmetic, working with alternating signs, keeping track of the value of the index. All of these little ideas that don't seem to be terribly important are actually very important, because we're seeing that every part of a problem is essential to getting to the finish line, so to speak. Okay, so that's a good example. Nice review for the BV technique. Now, these next 2 examples I wanted to use as a means of clarifying some examples or techniques that I've taught you during the semester. When you look at number 11, it basically says, use the rational zeros theorem to find all real zeros of the polynomial. Okay, and then factor it. Well, rational zeros is fine. You understand that. You would know that any rational zero, the numerator p would have to divide the constant term, and the denominator q would have to divide the leading coefficient. And that's fine. But I always told you to look for obvious zeros to cut down on the amount of work, because otherwise, you spend a lot of time doing unnecessary work. You can check for alternating sign or the same all non-negative and stop and use the boundary conditions. But what I'm seeing here is that this is a good indication of checking 1 and -1. 1 and -1 are always easy to spot. And what you can see here with the -1, notice we get the -5 minus the 9, which is a -14. And with the -1 here, we get the 6 plus the 8, which is a 14. So we're like, okay, I'm done. I'm not worrying about writing down a bunch of fractions and checking them when I don't need to. So this is a clear indication of utilizing a little bit of observation to move the problem forward. So now we have that f of -1 is actually 0. So what we can do is use the power of the synthetic division to move the problem forward. So what do? We simply write the coefficients down, 5, -9, -6, and 8, and then we use the 0, -1. So this basically activates the division algorithm in a way that's convenient when we have a monic polynomial of degree 1. So we have the -1 here because we've shown that it's a 0. And so we bring down the 5. 5 times the -1 is a -5, plus a -9 gives us a -14. And then we multiply again. -14 times -1 is a +14, plus a -6 gives us an 8. And then one more time, 8 times the -1 plus the 8 gives us the 0. So we knew this was the case, but what the synthetic division does is it provides us with the reduced polynomial. So now we're doing 1 and 11 and 12, and they're turning out to be the same problem, the factor theorem. So we have x plus 1 times 5x squared minus 14x plus 8 equals f of x. But now, of course, we're done with rationalizing theorems. We're done with synthetic. All we need to do is try AC. So here with AC method, we have 5 times 8. But noticing that 5 and the 8 wouldn't be any good for the -14, we observe that we can break down the 8 as 2 times 4, 5 being a prime number. But then, of course, if we group the 5 and the 2 to get a 10, coupled with the 4 and 2 negatives, we get the -14 that we need here. So the AC method will work in this case. And then, of course, we can factor by grouping. Just rewrite the -14x as a -10x minus a 4x. And then, of course, here we can factor the 5x to give a 5x, x minus 2. And here we can factor the -4 to get -4 times x minus 2. So again, basic factoring from college algebra. And so now we have x plus 1 times 5x minus 4 times x minus 2. Now, if you like, you can just use zero product. We already know we have -1. This will give us a 4/5, and this factor will give us a 2. Now, when we look at this, we're thinking that's a factorization, but the complete factorization that we did with the C's and the A, we can factor the 5 here and then put in all the negatives. So we have 5 times x minus the -1 times x minus 4/5 and times x minus 2, where we have all of the zeros available here, -1, 4/5, and 2. So again, we don't always have to jump on the bandwagon of a theorem if we can actually see something that's simpler. And you always want to check for easy zeros. That saves you an immense amount of time, and then you can focus more so on the arithmetic. A lot of times when you start checking with the rational zeros, you don't focus on it and you drop a sign and then you miss a 0. And so give yourself a breather and checks for obvious zeros here first, always. Now, for the next problem, it's basically the same thing because of the way I tried to do it, but these are very important concepts. These are central to mathematics, the factor theorem. So what it has here, it says, use the factor theorem to determine whether x minus c is a factor of f of x. Well, first, what we do is we got this. We have x plus 11/5. So the 0 would be -11/5. So we can do what we did for the last one to show that -1 was an actual 0. We knew it was, we just wanted the reduced polynomial. But here, we don't want to substitute -11/5. We want to do it the slick way by the synthetic division. So we can take this polynomial, say, if this is a factor, then we must know that -11/5 is actually a 0. So we can affect, again, the synthetic division. We have the 15, the 23, the -42, and the -44 here. And then we can put our 0 here, that is the negative 11 over 5 at this point, and then start the synthetic process, just like we did up here. So we bring the 15 down. Notice when we multiply by 15, the 5 absorbs into the 15 to give a 3, and we have 3 times negative 11, which is a negative 33, plus 23 gives us a negative 10. Okay, let's do the process again. 5 absorbs into the negative 10 to give us a negative 2. And so in this case, we have a negative 2 times a negative 11, which is a positive 22, which we add the negative 42 to give us a negative 20. How simple is this? And then, of course, 5 divides the negative 20 to give us a negative 4. So we have a negative 4 times a negative 11, which is a positive 44, which absorbs the negative 44 to give us a 0. So we're like, cha-ching. So it's like, you know, you can substitute the old-fashioned way, or you can use the synthetic and save yourself a lot of time. And then we see, by virtue of the factor theorem, we know not only that this is a factor, but we verified the 0. So it's a twofer, so to speak. So indeed, x plus 11 over 5 is a factor, and that's the reduced polynomial right there. And so we could finish this problem off like we did that one. So again, take advantage of the factor theorem. The factor theorem is a powerful tool that again, we do it without thinking about it on just basic problems, but on other problems where we're maybe focused on other things where the factor theorem is not mentioned, we should try to use it, just like we did in problem 11. Now, one thing that we found to be kind of useful here in our work is the use of inverses. We know with the inverse trig functions, that was an incredibly important part of our study with trigonometry and how it impacted solving trigonometric equations. The inverse trig functions are rich in calculus and analysis, and so you will see that as you take the calculus sequence. But in this particular problem, we're back to the algebraic part. We have f of x is the principal square root of x minus 2. So what we want to do is just figure out the inverse function and some of the properties that we have of the inverse function and f itself. So first, we just notice here that for this to be well defined, x must be 2 or greater. And then, of course, it's the principal square root. So the least value is 0. And then, of course, it can be infinitely large. But now, of course, this is a one-to-one function. You could prove that using the definition. But this is something we did often when I was reviewing the one-to-one functions back at the beginning of the class. And so now we know that the range and domain between f and f inverse just flip. So now we see the domain of f inverse is the range of f, and the range of f inverse is the domain of f. So that's a freebie. Now, of course, this is just a right shift by 2, so f of x looks like that. So we know that f inverse would have to look like that, but let's just write it down. We know by the reflective property, if we use the same independent variable x, then we get this nice reflection in the line y equal x between the function and its inverse. So of course, y would be the square root of x minus 2, and then we can square. So this will give us y squared equals x minus 2, and solve for x by adding 2 to both sides. This will give us x equals y squared plus 2. And now, of course, it's convention just to say, okay, let's write everything in the independent variable x. So we replace the y with the x, and we have f inverse of x is just x squared plus 2. And then, of course, you can easily draw the function and its inverse just using a couple of points in the reflected line there. So again, I can't underestimate the use of symbolic calculation that we see with synthetic division and the use of just the concept of inverse. We really do, you know, if we didn't invent inverse functions, we'd have to of necessity, because we have to communicate between different spaces. And when some of you that go into computer science will figure out that, you'll define functions in your algorithms to communicate with different parts of your code. and values will be passed back and forth between different subroutines. It's an amazing use of calculus and just the concept of the function. Again, what's the old saying? Necessity is the mother of invention. Absolutely, absolutely. As times change, we have to invent new ideas and new ways to get things done. So let's look at the next problem. Now, think about this just like you're doing WebAssign. If there are formatting issues or formatting directions, do that. If no approximation is requested, that is nothing is said about any approximation, then you write an exact answer. You go over to the palette. If you need a square root of 2, use the square root symbol. If you need a pi, then you go to the symbol for pi. I mean, everything is exact, and I I focus on that. So the final exam should focus on that concept. It is important to be able to write clean mathematics, and I'm impressed with what I've been seeing. So continue to do that. Now, let's look at number 14. This one actually gives us a little hint. It says solve the exponential equation, but express the answer in terms of the natural logarithm, in the sense that we could use any base we like, but we're thinking, all right, well, maybe WebAssign wants a decimal approximation. And I mean, otherwise we might have to use the change of base formula. So let's just go ahead and use the natural log here. So when we look at this problem, we have 4 to the x plus 4 equals 5 to the 2x plus 5. And this is where I'm saying you might be inclined to use a base 4 logarithm or a base 5 logarithm. It wouldn't matter. The answers would be completely equivalent due to change of base. But we're just going to take natural logs of each side and use the power rule. So if we take the natural log of both sides, we can bring the power of x plus 4 to the factor, and we can bring the power 2x plus 5 to the factor, which multiplies ln 4 and then ln 5. So the power rule incorporated with taking natural logs gives us this equation, which is now set for the natural logarithm. So what we can do is just multiply things out. We'll get x times the natural log of 4, and then we'll get 4 times the natural log of 4 here. And then on the right-hand side, we have the x times the 2 times the log of 5. So I kind of write the x over to the left so we can see its coefficient here clearly. And then, of course, we have 5 times the natural log of 5. So we've seen this many times before. Now it probably appears to be pretty simple. So just get all the values of terms with x on one side. So this means from the log 4, we'll have to subtract the 2 ln of 5, which we have here, of course, with the x factor. And then, of course, the 5 ln of 5, we need to subtract from that 4 ln of 4 to retire all of the non-x terms to the right-hand side. And then, of course, now we just have a coefficient times x equals this real number, so we can divide by the coefficient. So that would mean that x would equal 5 times the natural log of 5 minus 4 times the natural log of 4 divided by the natural log of 4 minus 2 times the natural log of 5. So again, we have an exact answer, and if necessary, we can use our Google calculator to get a nice approximation of this if the client so desires. So again, the exponential functions are our friend. They behave very nicely, and then you can just take this number and put it in the solution set. So again, we spent a lot of time reviewing techniques of solving equations, especially with logarithms and exponential functions. And you will continue to use that. Sometimes you'll have an easy equation to solve in calculus and you're like, oh man, it was harder when I took Professor Ron's pre-cal class. And that's fine. I want it to be simple. Yeah, I want you to remind me of the student who said, because I took Professor Ron for pre-cal, calculus was easy. And he said, well, let me just tell you this, pre-cal is a hard class, but it gets you ready. And so I was glad to hear that he finished up his engineering degree and was very pleased that he spent the time preparing for the calculus, because that's the whole idea. let's keep it nice and easy. We sometimes it's nice to enjoy class, actually, that you know what you're doing and that you don't have to start from scratch. Okay, now before we get to the trig graph, which we'll do some more transformations, let's solve one more log equation. And so we have the base 4 logarithm of x squared minus 3x equals 1. And you're thinking, well, Professor Ron, I can do that in my head. Well, maybe you can. So notice, what's the logarithm? It's the power of the base. So the power of 4 that equals x squared minus 3x is 1. So we have x squared minus 3x equals 4 to the first power. So now we can simply retire everything to one side, and that'll give us x squared minus 3x minus 4 equals 0. Well, of course, wouldn't it be nice if everything was so easy to factor? We can use a -4 and a +1 to get the -3. So the x minus 4 times the x plus 1 will be suitable for that. And then, of course, by a zero product, this will give us x equal 4, and this factor will give us x equals -1. Now, of course, what I've written here, and this is important, the original equation must blend with these values of x. And because of the square here, both of these values work fine. And so what I've written here is both values are valid. So I think you've gotten pretty good at this. Just remember, when you're solving logarithmic equations, there's always the possibility that you can introduce values of x that do not solve the original equation, kind of like squaring in an algebraic type sense. Just be careful for that, that you make sure that both of these actually do solve the original equation. So both of these would be valid. Now, for the next problem, like I said before, you might have an example on the final exam where you get to use your understanding of transformations in the context of a trig graph. So for instance, it says, use vertical shift to graph. Well, use Professor Ron's technique to graph. Now, of course, as you get better and better at this, you can compartmentalize a lot of the formality and move a little bit quicker to the punch line or to the finish line, and that's fine, and I'm all for that. So for instance, we have 2 times cosine of 1/2 x plus 2. Now, these are fairly simple transformations, but we notice that in order to get principal points and not just kind of, guesstimate the answer, we can break this down into 3 transformations. First, we start with the parent function and we replace x with 1/2 x. Well, the 1/2 x is basically going to be a horizontal stretch by 2 because the 1/2 is between 0 and 1. So this is going to make the period actually larger by a factor of 2. So we're used to 2x and 3x making it smaller. Here we're actually enlarging it. And then for this particular coefficient, we're multiplying the function by 2. So this will be a vertical stretch by 2, easy to do. And then, of course, we're adding 2 to the function, and that will be an upward V shift by 2. Again, the last two be very simple to visualize and also to do algebraically. So now what we can do is say, okay, let's just start with the simple points because we can move them around very easily. The 0, 1, the pi over 2, 0, the pi -1, the 3 pi over 2, 0, and the 2 pi 1. And so what we can do is say, all right, well, the first thing we want to do is do the h stretch. So all of the x coordinates get multiplied by 2. So of course the 0 stays 0, pi over 2 becomes pi becomes 2 pi, 3 pi over 2 becomes 3 pi, and 2 pi becomes 4 pi, but that makes sense. 2 times 2 pi is 4 pi, so we get the period that we expect. And of course, the numbers here stretch across a standard period. That's why I choose them, because they're easy points and they're spaced equidistantly. So that just makes for a simple graph, and we do this because we like simple. And then here, the v stretch by 2, that's basically going to multiply all of the y coordinates by 2. So the 1 becomes 2, the 0 stays the same, the -1 becomes -2, 0 stays the same, and the 1 becomes 2. And then lastly, we just do an upward V shift by 2. So we have to add 2 to all of the Y coordinates. So again, the 2 becomes a 4, the 0 becomes a 2, the -2 plus 2 is a 0, the 0 becomes a +2, and then of course 2 plus 2 is 4. And so now here is the new function right here. At least by determining these 5 points, we can get a real simple graph. And again, that's all you need. You just need one period, because we know that replicating this function infinitely will produce the infinite function. So now we have a 0, 4. We have, again, we've got the principal points here on the x-axis. We have the pi 2, we have the 2 pi 0, 3 pi 2, and the 4 pi 4. It's just like when we do the common denominators. We keep it simple so we can shift things in an easy fashion. So there's our distinct period of this function, and we're good to go. So again, just remember that transformations are universal, and you will continue to use them, ladies and gentlemen, as you take more science, more engineering, more mathematics. The transformation properties you will see with infinite series, with sequences. I mean, it's going to be amazing how often you use these skills. Again, what we teach you in the pre-calculus are the essential skills for understanding the calculus. So you will see this as you work through the calculus sequence. Now, let's look at, of course, the favorites. Professor Ron likes the inverse equations. So let's look at number 17 and number 18. Now remember, when you take your tests and you do your semester test, they're long, you know, I mean, in the sense that you get lots of questions on very similar topics, and, you know, you work them out. Just remember with the final, you know, it's a comprehensive test, and you've got a finite amount of time. So the survey is along the basic concepts and structured in a way that the calculations aren't super laborious. So just remember that you will be practicing standard techniques like induction, the binomial theorem, function transformations, logarithmic equations, rational zeros, factor theorem, all the basic constructs, okay? So a very popular construct was the inverse equations. That is the inverse cosine of 4 pi over 3. And again, I know you made your note cards. And when you look at the inverse cosine function, we know that it's defined, output is 0 to pi. And so we can't apply the inverse equations directly, because 4 pi over 3 is not in the output of the inverse cosine. So we don't worry about it, because we live for reference numbers. We live for reference angles. Always push everything to the first quadrant and attach the appropriate sign. Use the arithmetic of the unit circle, and you will never go wrong. You can't, you use a fancy calculator and you won't even understand how to use it, and put nonsense down. That's what I don't understand. The thing is that your brain is the most powerful tool that you have. So I want you to use it. So notice here that this is bigger than pi, but smaller than 3 pi over 2. So this is in the third quadrant. So what we want to do is move it to an equivalent value. So let's do the reference number and attach the negative sign, because the cosine is negative in the third quadrant. So we'll have the negative of the cosine of pi over 3. And now we know with the cosine function, we can negotiate the negative by using the identity pi minus inverse cosine of pi over 3. So this negative, we basically remember, we have cosine, inverse cosine. This is on your note card, of negative x is just pi minus inverse cosine of x. So now that's the x right there. And so we just get inverse cosine of pi over 3. But this gets the check, because the pi over 3 is between 0 and pi in the output of the inverse cosine. So now we get pi minus pi over 3 using the inverse equation here. And of course, that gives us 2 pi over 3. So again, like I say, the biggest tool you have, the most efficient tool you have is your brain. And it will direct you better than punching on a device that you probably paid too much for. I don't even want to know how much you all paid for some of these calculators. It's ridiculous. Now, for 18, as we see here, we're thinking we can still apply the concept of the inverse trig function, but in an algebraic way. Now, let me make a comment here. Notice how the directions say x is positive and in the domain of the inverse trig function. Well, we know that has to be assumed. That has to be assumed if we do these problems. And then it's saying that x is positive. Well, we don't need that. I mean, in this particular example, we'll see that x could live anywhere between negative pi over 2 and pi over 2. But if it's given, fine. We just make sure that our answer supports that, and it will. So when we look at this particular problem, we think, okay, well, we have sine of the inverse tangent of x. And what's our technique? Well, we want to introduce the right triangle that's involved with this inverse trig function. So we just assign it alpha or theta or beta or whatever letter you want for the angle. So applying the tangent function or the definition of the inverse tangent, this will give us x equals tangent alpha. So basically, we need sine of alpha. Well, if we have this, then we can construct the right triangle as opposite over adjacent. So we have x over 1, opposite over adjacent. And then by the Pythagorean theorem, we just have 1 plus x squared square root. Now we can define sine of alpha as the opposite over the hypotenuse. And so we're here. And we see that the sign of this expression is carried by the x. So it would not matter if the x were negative. So that was, again, it doesn't make the problem better or worse. It just wasn't necessary. But a lot of times these hypotheses will be introduced just to keep you on your toes. But we would not need that because the sign would always be carried by the x, and this would be well defined. So again, you're thinking, when do you use this in the calculus sequence? Mainly you will use this in calculus 2. Not so much in calculus 1, but you will focus on the hyperbolic functions at the end of cal 1 and then get into the inverse trig functions in cal 2. But again, we can study all of our power series with the natural exponential power series, the inverse hyperbolic, and the inverse trig, and be done with everything. It's amazing. You're going to see all this stuff come together with the sums and the series, and it'll be really neat. Now, we solved a bunch of equations. So maybe we'll have one equation on the final with trigonometry. And then often, ladies and gentlemen, you've kind of been schooled by Professor Ron to always write down all the solutions just to keep safe, make sure you cover them all. And then you might be asked to restrict. So it's probably better to look at all the solutions and then trim it down based upon the values of k. That's basically how I taught you. So we've got the equation 2 sine squared equals sine x. And of course, this is good. You don't have to use any fancy identity. I know you can use them, but this is not required here. Notice if we subtract the sine, we get 2 sine squared x minus sine, which we can easily factor. So I'm going to factor the 2 sine x out of each of these. So that'll leave me behind a sine x with this term, and obviously a minus 1/2 here because this doesn't have the 2 in it. So now we've got zero product. The 2 doesn't matter. Divide by 2, it doesn't have any impact on the zeros. So we will have sine x equal to 0 by zero product, or sine x equal to 1/2 by zero product. And then, of course, this is old hat. We're just on the x-axis, right? So 0, pi, 2 pi, 3 pi, just multiples of pi for the 0. The easy ones are when we're on the axes. No Professor Ron's lemma. And you're thinking, yay. Okay, now, of course, we're back to Professor Ron's lemma, we have sine x equal 1/2. We know the inverse sine of 1/2 is pi over 6, and we can extend that by multiples of 2 pi. And then by Professor Ron's lemma, the other solution in the upper arc will be pi minus pi over 6, which is 5 pi over 6. We've done that a million times. And then, of course, extend by multiples of 2 pi. So this will correspond to all the solutions, and we could just fit them in the curly braces and be done and separate them by commas like you did in your WebAssign. But now what we want to do is just restrict, because we need to live here. So first, we can get the 0 when k is 0, and we can get pi when k is equal to 1. But of course, 2 or negative 2 would take us out of this, so we're done with that. And then, of course, here we clearly have pi over 6 and 5 pi over 6 when k is 0. But of course, when we start to add multiples of 1 or negative 1, these go outside of this interval. So the only solutions that we have in this particular case are 0, pi, pi over 6, and 5 pi over 6 that actually exist in that interval. So again, the basic equations and even the harder equations, even though they may take more time to do, they're not more complicated because we keep recasting the same fundamental concepts over and over. The inverse trig functions basically allow us to understand how we define sine and cosine and tangent from the beginning. I mean, everything is all tied to the unit circle. So if you start to waver, go back to the unit circle, and ground yourself. Don't make it up. There's no need to make it up. Okay, now the last few problems, there's one with a law of cosines, and then we've got a conic section, and then a little bit with the new stuff. So this next example is kind of maybe not a personal favorite. I'm not a big fan of the triangle theorems, but I like the exact computation that we learned how to do with them. And that was the best way to introduce Professor Ron's lemma with the law of sines in the ambiguous case. So that was worthy. But I just wanted to throw in a little triangle problem. You know, again, these are simple and fun to do and then useful in physics and engineering. So we have the distance from home plate to dead center field in Sun Devil Stadium. Again, straight out to center field is 401 feet. And then it says a baseball diamond is a square with a distance from home plate to first base of 90 feet. It says, how far is it from first base to dead center field? Well, that's just a law of cosines. Again, you've got, if you think of extending over here to third base, you just simply cut the 90-degree angle in half here. So you can think of third base over here, if you like. So I can say third base. Again, this would be a 45 too. Same calculation. It wouldn't matter if we did it on this side either. So there's nothing special about the first base. We could have used third base. So now we just basically have a distance, basically a c squared equals a squared plus b squared minus 2ab cosine theta, but I've replaced the c with the d. So again, we have an a of 90 and we have a b of 401 and we have a theta of 45 degrees. So again, not very beautiful numbers, but we still can do symbolic calculation and then use the Google calculator. So again, we've got the 90 squared plus the 401 squared. And then of course the cosine of 45 degrees is 1 over root 2, which will absorb into the 2 to give us a root 2 times 90 times 401. So at this point, you could just square root this or you could factor this. There's really no plus to doing either. But a lot of times if you factor, you can find some interesting arithmetic, but I didn't find any here. So you get 401 times the quantity 401 minus 90 times the square root of 2 plus 90 squared. And then of course, we'll take the principal square root. And here is the exact answer, but you can actually approximate this with your Google calculator, getting a nice calculus approximation. which will give us 343.31. And what I said here is just round to 1 decimal, and that'll give you 343.3 feet from first base to dead center field. So again, not a very interesting problem, not a very hard problem, but certainly reminding you of the triangle theorems. Now, the next problem, this one's kind of interesting. It says use the center, the vertices, and the asymptotes to graph the hyperbola. So this is like an example of, okay, well, you know, let's just see what we know about hyperbolas. But what's nice about this problem, and of course, you know, you're thinking, am I going to have you complete the square? Well, I might give you a problem where you've got to complete the square and figure out the h and the k, and then the vertices like you did in your WebAssign. So that would certainly be a good problem that would cover all the bases. Notice in this case, the squares are complete. So what we see is that we have an h in the translation equation of 2 and a k of -1. So the translation equations will be x prime equal x minus 2, y prime equals y plus 1. And then, of course, solving for x and y, x is equal to x prime plus 2, and y is equal to y prime minus 1. So again, of course, here, h is 2, k is -1, as we see here. And then a is 2, and b is 3, as we've got here. So if you like, we can just go ahead and write down the equations for the asymptotes and then the equations for the vertices, if you like. Just remember that c squared equals a squared plus b squared. We're going to use that in the rotation example that I have for you. So now, of course, in the translated system, y prime is equal to what? B over a plus or minus b over a times x prime. Of course, now because the x term is squared, so we know that the foci are distributed on the horizontal axis, or as what they call the transverse axis. And so now this is in the translated system, but we can use the translation equations to actually write this in the old system. That is, y prime is y plus 1, and x prime is x minus 2. And so here, if we looked at the positive root here, or the positive sign, we'll get y is equal to 3/2 times x minus 2 minus the 1. And then, of course, here, the 2 is absorbed, leaving us with a -3. So that'll give us 3/2 x minus a 4. And then, of course, if we use the negative here, then we'll have a -3/2 x. And of course, the 2 is absorbed, but that leaves us with a +3. So a +3 minus 1 gives us a +2. And then, of course, the -3/2 x. So these are our asymptotes using the translation equations. Now, of course, because the vertices are situated on the positive axis or the horizontal axis, we've got the b prime plus or minus a0. So now we can get the x's and the y's here just using the translation equations. So we'll have plus or minus a plus h. And then, of course, we've got 0 minus a 1. So this will give us the coordinates for the vertices. Of course, a lot of times you just take the center and you go 1, 2 in each direction, which is fine, which I'm sure you do often. But these can all be done algebraically. And so, of course, we can get 4, -1. And then with the subtraction, we get 2, -1, which again, are distributed on either side of the center. 2, -1 here. So again, that, and then of course, if you wanted to find the foci, you can use this equation. Again, that would just be the square root of 13 for the c. So just write down here, c is square root 13. So now, and sorry, that's a equals. So now, we can go ahead and draw the box, so to speak. We've got the vertices, and then of course we can ascend and descend 3 to get the other points on the opposite sides of this rectangle and dot in the rectangle, and then get nice diagonals for the y equal 3x, 3/2 x minus 4, and then of course the y equal -3/2 x plus 2. Now, of course, in the center here, when you think about this, this is the new axis here through the center. This is the x prime, and this is the y prime. So again, we can write all of these in the old system and just in the new system and use, this line would be 3/2 x prime, and this line would be negative 3/2 x prime in the translated system. WebAssign often just wants you to give the asymptotes in the old system, just to have you practice with this. So that's kind of the theme that WebAssign gives with the translated equations. So again, kind of a nice problem that covers all the bases. I think that the translation equations are kind of nifty, and you should always think about the new set of axes, x prime, y prime, from these set up here. Okay, now let's complete and look at the last couple of examples. Notice for the last couple, or the last four, we're utilizing some of the newer constructs. The first one here, again, both of these are geometric. I would recommend that you review the arithmetic, even though it's very simple. It makes for a good test question just to compute a common difference and an nth term or whatever. But the geometric, of course, I have emphasized to a great deal because of the importance in calculus. You can't get too much work with the geometric series. So for the first one, we have I equals 1 to 5 of, in this case, 3 times 3i. Now, when you look at this and you think, 1, 2, 3, 4, 5, and you think, just think of it, 1, 2, 3, 4, 5. That's 5 terms. And you look at this and say, well, wait a minute, I need to write this in a way so that I can, keep track of all the terms, so to speak, because this doesn't look like the general form that we derived. So when you look at this, you're thinking, okay, I does start at 1 and ascends to 5. That gives me the n, but I need the I minus 1. That's what we actually derived as our conventional summation. And so in order to make all of the A's and the N's and the R's work, we need to introduce the I minus 1. So what we can do is borrow a 3 here. 3 times 3 is 9, and then write 3 to the I minus 1. And this gives us the convention that we used in our derivation. So that's important in the sense that you can write it out and then figure out everything and count up the number of terms, which is fine. That's a way to do it. Or you can construct it so that we get the actual convention with the summation. And if you stay inside the sum, you must write it this way. And so now we see that n is equal to 5. I can just go ahead and write this out. I do write extra stuff on the notes, on the solutions. We have n equals 5. We have a is equal to 9, and we have r is equal to 3. So all of that is set up. The partial sums with the geometric are a lot more complicated because you've got to keep track of how many terms you have, and you have to write it in a way that you clearly know what a and r are. I mean, that's always the case, but the n is always a problem with students. So now you have a times 1 minus r to the n divided by 1 minus r. And so we just fill all this in. A, 1 minus r to the 5, 3 to the 5th, and then we have 1 minus r, 1 minus 3. Now notice, in this particular case, that the negative here is upstairs and downstairs, so we can just multiply and divide by -1 to turn everything around. No reason to carry 2 negatives around. So now, when we look at this, we see 3 to the 5th power is 243 minus a 1, and then of course 3 minus 1 is 2. So this is going to give us a 242 divided by 2 times 9. And then, of course, if we divide by 2, that will give us a 121, and 9 times 121, which is easy to do, that'll give us a 9, and then, of course, an 18 with a 1. 9 plus 1 is 10, so we get 1,089. Again, how you decide to set up your partial sums for geometric sequences is often a very personal thing. But if you're going to stick to an actual convention, then as you write on your note cards, you need to make sure you respect that convention, because if you don't, then your n will be off. And if the n is off, you don't get the right answer. So again, this is how I set this up and prove this for you. And it's important that we adhere to it. You can always re-index. You can always redo things. We see the binomial theorem is a little bit different. It always starts at 0. So we have to respect that if we're going to do n choose k, and where k starts at 0 and ends at n. So that gives us n plus 1 terms. So there's always something to deal with convention. We see that so much with conic sections, and it's no different with the geometric. Now, look at the next problem. This is actually an easier problem. It says, find the sum of the infinite geometric series if it exists. Well, we start with 5, then we have a negative 5 over 4, a positive 5 over 6, minus a 5 over 64. Okay, well, when you look at this, this is clearly geometric, because if we start with a equal to 5, then we multiply by a negative 1/4 to get negative 5 over 4. And if we multiply by another negative 1/4, we get 5 over 16 with the positive. So we can see that we have a well-defined A and a well-defined R. So again, we move to this convention and we say A, and we have negative 1 over 4 to the I minus 1, I equals 1 to infinity. Because when I is 1, we just get 5 times negative 4 to the 0, negative 1/4 to the 0, which is 5. When I equals 2, we get 5 times negative 1 over 4, which is this term. So this works. Now we're like, don't have to worry about an end here because it passed to infinity. So we have A is 5 and we have R is negative 1/4. So now we have A divided by 1 minus R. So we have 5 divided by 1 minus the negative of 1/4. So that gives us 5 divided by 1 plus 1/4, which gives us a 5/4. And of course, if we reciprocate and multiply, the 5's absorbed and we get 4. So again, the infinite case is so much easier. And then of course, remember with the infinite case, R in absolute value, this will be what you'll use heavily in calculus too. R in absolute value must be less than 1 for this to converge. And you will actually do more theory with this in calculus too. And it will bear heavily on the power series that you compute. Again, this is a very important object in analysis, the geometric progression. Now, with the last couple of problems here, these allude to the mathematical induction and the binomial theorem. So on the test, you should expect an induction problem and a binomial theorem problem, and that's about all there's room for. So you look at that and you say, okay, well, that's good. I'm glad the final exam is cumulative because there's less problems, and you know, that kind of makes it for a plus here. So this one is actually one that I did in class where we had the divisibility problem. And it's done the same way. Notice they give you a hint here, but the hint kind of takes away adding and subtracting the terms. So I'll show you how you get that. If you just start with this, it seems like something got left out. So it says, use the principle of mathematical induction to show that the statement 5 is a factor of 7 to the n minus 2 to the n is true for all natural numbers. So remember, we did a divisibility argument in the lecture at the last week with induction. So what we can do here, and this of course is where I fleshed out the hint instead of going directly to it, which didn't make any sense if I left this line out. So I'll approach this just like I did in lecture. So our logical statement will be 7 to the n minus 2 to the n is a multiple of 5 for n greater than or equal to 1. And so again, we can check lots of values of n and say, oh, well, it appears to be true. But then, of course, the induction will give us that extra edge to verify for all natural numbers. So first, to get going, we think, well, we got to have some reason to move forward. Let's check one. Does it even work for one natural number? So when we check one, it clearly does, because we just have 7 to the first power minus 2 to the first power is just 5. And of course, 5 is 5 times 1. 5 is certainly a multiple of itself. So we get P of 1 is true. So now, in the next case, the arbitrariness is what we have to use. We need the domino effect. We want to see if we assume it true for some natural number, then it'll just fall into the next natural number and knock it out in a good way. So we assume now, again, we can switch to K. You don't have to. We found that that's just cosmetic. We could say that 7 to the K minus 2 to the K is actually a multiple of 5 for some integer T. That's our induction hypothesis. So we assume the multiple of 5 for some natural number K. And then what we want to do is use this hypothesis like we did last week to show that if we bump up to the K plus 1 power, that knowing this will allow us to show that this is actually a multiple of 5. Okay, so in order to do that, we don't really have the powers of K here that allow us to use this. So the algebraic maneuver has to do with adding and subtracting a term that I call convenient. So of course we need a 2 to the K, but we don't need a 7 to the K because we want to be able to factor and leave something behind that will actually leave this behind. So when we do that, we add and subtract 7 times 2 to the K. This will work. Other expressions will work, but this is the quickest way to do it. And then once we have this, we can factor by grouping. Notice here we have a 7 to the K, and, well, excuse me, you have a 7, the 1 here, a 7, and a 7 here. So we can factor the 7 from here and here and leave behind 7 to the K minus 2 to the K. Here, let's do the same thing. We've got a 2 to the K and a 2 to the K, which we can factor from both expressions, leaving a 7 minus 2. Okay, well, first, when we look at this, we're like, does this help us? Absolutely, because that's the induction hypothesis right there. So now we can bump up here and say, okay, well, 7 to the K minus 2 to the K is actually a multiple of 5. So we can replace this with 5t by the induction hypothesis. And then, of course, 7 minus 2 is 5. So that's just as good, even easier. So now we have a 5 here and a 5 here, which we can factor. So what's left behind is 5 times an integer. That is 7t in this case, plus 2 to the K is just a natural number. And we see that this expression, 7 to the K plus 1 minus 2 to the K plus 1 is just a multiple of 5, just like we were saying it was up here. So now we see that P of K plus 1 is true. That is, we have the domino effect. We assumed it true for K, and then it just falls into the K plus 1. And then, of course, K plus 1 falls into the K plus 2. So we get the coverage of the entire natural number system. So now we're done, because the induction principle says if we can show that for some initial natural number that P of n is true, and by assuming that P of K is true, that implies P of K plus 1 is true, then we've covered all the bases. And then by induction, we know that this particular statement is true for all natural numbers. So again, I'm sure induction is somewhat awkward and odd to you, but it is something that you encounter in calculus, especially with Riemann sums in Cal 1 and with sequences in the monotone convergence theorem in calculus 2. So you do need to be aware of it. It's not one of those kind of like, well, you know, it's not going to be the end of the world if you haven't seen it, but it certainly will make life a little bit awkward and maybe hard to understand if you've never heard of the concept, the inductive concept. Now, for the last problem for the review, this is an example of the binomial theorem. And so what we have, it says the coefficient of x to the fourth in the expansion of 3x plus 4 to the 6th. Okay, so this is where I had a student during the office hours, conference hours, say, well, do we have to do the entire expansion? And I said, no, this is like what we did in class. What we do is figure out which term has the x to the 4 expression in it, and then we calculate that particular term. So let's write it. So when we look at this problem, we have 3 to the x plus 4 raised to the 6th power. So n is 6, and k will run from 0 to 6, giving us 7 terms. And so now, of course, we have a raised to the 6 minus k, 3x to the 6 minus k, and we have 4 raised to the k. Now notice, when do we get the x to the 4th term? Well, that would have to be when k is equal to, because that will give us 3x raised to the 4th power, which will give us a factor of x to the 4th. So we have x equal 2. So we're going to figure out the coefficient of x to the 4th by using k equal 2. So we take the k equal 2 term from this sum. So again, k equal 2 will give us k choose 2, 3x raised to the 4th, and then 4 raised to the 2nd power. So now, of course, when we do the binomial coefficient, we do the falling factorial. So we have 6 times 5 divided by 2, or 2 times 1, 2 factorial. We have 3 to the 4th power, which is 81, x to the 4th power, which is x to the 4th, and 4 to the 2nd power, which is 16. So what I did here first is I absorbed the 2 into the 6 to give a 3 times 5. So that's a 15 times a 16 times an 81. The x to the 4th just kind of comes along for the ride. We don't forget it, but we don't have to worry about it. So now notice here, this is just really 15 times 15 plus 15. If you think of 16 as 15 plus 1. So that gives you 225 plus 15. And then, of course, 81 is 80 plus 1. So if we write it this way, the arithmetic is easy. So we have 80 times 225. We have a 1 times a 225. And then we have an 80 times a 15 and a 1 times a 15. All simple numbers. So here, if we hit the 225 with 8, we get 1800, tack on a 0. The 225 is as it is. And then, of course, 8 times 15 will give us 120, tack on a 0 to give us 1200, then the 15. So now, of course, if we add these two numbers, that'll give us the 18225, and then, of course, 1215 right here. So the symbolic calculation helps you to compute the products very easily. And so now 5 and 5, that's a 0. Carry your 1, then we have a 2 plus a 2, that's a 4. And then we have a 2 plus a 2, that's a 4. And then we have a 1, well, how simple, 1 plus an 8, which is a 9, and then a 1. So we have 19,440 x to the 4th. So the coefficient of x to the 4th is 19,440. So again, a simple problem. Basically, read the example. If you've got an n equal to 50, and they say, what's this term? Then you just pick off the term. And I mean, what do you want to write down 51 terms? That'd be crazy. So again, use the power of the theorem to locate the particular expression that you want, the particular term, and then that will save you tons of time. You might just have a problem where it says expand this, okay? And that's when you can use Pascal's triangle for numbers that aren't n's that aren't too large, like maybe 6 or 7, so to speak. Past that, it gets a little bit difficult, but it's still doable. Okay, so that culminates the actual work with the review. And what I wanted to do is just give you a little glimpse at the rotation scheme. And it's very doable. I mean, when you think about this particular kind of problem and what we do with it, it's kind of nifty. So what I wanted to do, again, if we add another day to this class, or like take out an SLO or something and revise, we can do this, but this is kind of like a little parting thought, and if you think this is interesting, you should look in your ebook when you have some time, or go on Wikipedia and look at rotation of axes. You can actually do this with linear algebra techniques, which is really nice, even easier to do with linear algebra maps. So the idea is that before, if you notice here, I kind of wrote down the translation equations to give you the analogous equations, the x primes for the translation, the x primes for the rotation, the x and y for the translation, and the xy for the rotation. How are these different? Well, in one system, you're translating the axes with no rotation. Here, what we want to do is rotate the axes. Now, there's a very simple way to do this using basic trigonometry that's not difficult at all. It looks complicated, but it's very simple trig. So what we can do is think of rotating the standard axes into the new axes by an angle theta. Now the problem and the difficulty here is the theory requires that we figure out from the standard equation, that is when we write the standard equation, ax squared, this is the standard conic, bx plus cy squared plus dx plus ey, need to sharpen this, plus f equals 0. So that's a general conic. Now, we know if we don't have the xy term, that's a translated system. If we have x's and y's hanging out. If not, it's not translated. But if we have this xy term, that corresponds to the rotation, and that's where the problem is. That's where the difficulty comes in. And I'll show you what the result is. But again, this will be interesting. I just want to make sure that you see how we get these translation equations. So what we can do is just basically rotate the given system by theta. And notice, everybody, if we take the distance from the origin to the point P, written in xy and x prime, y prime, we can take this radial distance, like the radius of a circle, to be rho. And then, of course, the distance, angular distance from x prime to rho, we're going to call phi. So if we start out by looking at this right triangle right here, we see that x prime is rho times cosine phi right here. And we see that y prime is just rho times sine phi. Okay, so how do we get the x and the y into the picture? Well, we look at the triangle right here. So now x right here is going to be rho times cosine of what? Theta plus phi right here. And then y right here is going to be sine of rho times sine of theta plus phi right there. So two triangles, simple right triangle trigonometry, nothing complicated, very simple. You could teach your friends how to do this. And now what we can do is just say, well, x, we just expand this, the cosine of the sum, that'll be cosine theta, cosine phi minus sine theta, sine phi. And then, of course, when you multiply this out, you get x prime right here, and you get y prime right here. So x is x prime times cosine theta minus y prime times sine theta. For the second one, you just use the sum formula for sine, so you get sine theta cosine phi plus sine phi cosine theta. Multiply it out, you get y prime again, x prime and y prime. So y equals x prime times sine theta, and in this case, y prime times cosine theta. So this part right here, I wrote right here in this box. So I transferred all of this down here. So these correspond to these equations in the translation. Now, of course, we want to be able to solve for x prime and y prime in terms of x and y. So what we can do is just multiply by convenient values. Here, we can multiply this equation by cosine theta and the bottom equation by cosine theta. And that will give us x prime is x cosine theta plus y sine theta. Very simple algebra here. And that's this equation right here. And then of course, if we want to absorb the x primes, we can multiply the first equation by a negative sine theta and the bottom equation by a cosine theta, and these will absorb, and we're left with y prime equals negative x sine theta plus y cosine theta. Again, very simple calculations here that are easy to do. And so I'll tabulate this right here. So now we have the translation equations, rotation equations for x prime, and we have the translation equations for x and y and the rotation equations for x and y. Now, why is this any good for us? This we can already go ahead and use, but these are like, what do we do with these, Professor Ron? Well, here's what you do. What you do is you use these equations here to rewrite the original conic in terms of x prime, y prime, okay? So the theory says if you do that, you can determine the value of theta, which eliminates the rotation term. And if you can eliminate the rotation term, you can figure out the rotation angle theta. And so upon doing that, and it just takes a lot of algebra, but it's doable, you get that theta must be 1/2 times the inverse cotangent of A minus C over B, where the A, B, and C are right here, okay? So you're thinking, well, hallelujah, I can do that. I mean, I can do that, Professor Ron. So here's another thing too, ladies and gentlemen. The discriminant is invariant under the rotation. If you rotate axes, the discriminant in the old system corresponds to the discriminant in the new system, so there's no change. So parabolas are parabolas, hyperbolas are hyperbolas, no change, okay? You might just look at this and say, I don't know what this is. So what we do is say, okay, let's use our equations of x and y. So first, we're thinking we've got what appears to be a conic section, xy plus 9. We go up here, we've got the b is 1, and we've got the f is 9, but the a and the c are both 0. So now we substitute this into our formula for theta. Okay, well, then that's just going to be 0 over 1, which is 0. So the inverse tangent of 0 is pi over 2, because that lives between 0 and pi. And then 1/2 of that's pi over 4. So now, ladies and gentlemen, we see that the actual rotation of the axes was actually pi over 4 radians. So we basically did this and moved pi over 4 radians. Now, how do we figure out what the x prime y prime equation is? Well, we take our rotation equations and fill in the value for theta. And so we get x prime times 1 over root 2 minus y prime times 1 over root 2. Y will be x prime x prime divided by root 2, and then y prime divided by root 2. These are the values for x and y. And so now you're thinking, okay, well, I'll substitute this value for x and this value for y into the equation. And I erased all of this to do an extra equation. I tried to do 2 drawings here. This one went south, so I erased it and put something else in its place. But now when you factor the root 2's, you just get x prime minus y prime times x prime plus y prime. And that's the difference of squares. So you get 1/2 x prime squared minus 1/2 y prime squared equals -9. Divide by -9, and you get a hyperbola. That is, you get y prime squared divided by 18 minus x prime squared divided by 18 equals 1. That's a hyperbola. And notice that the foci are on the vertical axis because the y term, the y prime term, is squared, so they're this way. Now you're thinking, okay, all right, so a, b, c, they're all the same. So c squared is a squared plus b squared. So c equals 6. And then, of course, a squared is 18. So a is 3 root 2. So now you've got foci of 0 plus or minus 6. And you've got vertices of 0 plus or minus 3 root 2. So then you're thinking, okay, for this one, remember, we'll get y prime equals plus or minus a over b times x prime. But A and B are equal, so we just get plus or minus x prime. So you're thinking, oh my goodness, look at this, Professor Ron. The asymptotes turn out to be the conjugate axes, so to speak. So when you actually rotate your angle here, pi over 4, you get your x prime and your y prime, and then you can plot the foci on the y prime axis and the vertices. And then when you draw your little rectangle A and B, it's a square because A equals B. And so what we see here is that the asymptotes here are actually the y-axis and the x-axis of the old system. Isn't that amazing? And now if you wanted to, you could do what you do in your WebAssign. I'm sorry this is kind of messy. I sketched this out. I have other notes here, but I didn't want to give you my honors notes because they're a little bit intimidating. So I just scratched this out by hand. And so now when you look at this, you're thinking, okay, I can go ahead and interpret these points in terms of the old system. So in the old system, this point is just what? Negative 3, 3. In the old system, this point is just 3, negative 3. And so what you can see here is that what's neat about this is that this is exactly the same as the translation equations, but in this particular case, instead of moving around like this, we're rotating. So if you're interested in this, I would definitely put some time into this. You'll have a ball with this. It's fun. You got this. You can derive this if you want. I can give you some help with that if you need it. And then you can practice with this. Practice determining the A, the B, and the C, and then finding the theta. Look in your ebook, and then doing your transformation equations to transform the XY equation into the X prime Y prime equation. And so what's going to happen is that this will be non-rotated. That is, this equation will not have any X prime Y prime in it. This will be eliminated. So you see, as we go from here to here, no cross product term. So that's the key to the rotation. We're seeing that the rotation term is tied up in this term. So the Cartesian equations are kind of crazy. So I just wanted to share this with you so you could see the beauty of all of this, and that really a lot of this invariance and these problems, they're just long in the sense that once you make the substitutions, it's just a lot of careful algebra where you get to the formula. And then of course, if you show that the discriminant is invariant, you start here and end up here. So it's just long-winded calculations. They're not, and the thing is, ladies and gentlemen, they're not difficult calculations. It's what I call court reporting. And so you don't have to suffer through all of that to be able to use these equations. So I just wanted to share that with you as kind of a parting gesture that the rotation of axes is a really elegant pursuit in math. And again, some of you will probably take linear algebra, and you can actually address this strategy using linear transformations, which again is really, really nifty and doesn't seem to be as hard as this. But again, it's an interesting discussion. And again, if you're interested in it, please pursue it. Go to Wikipedia or go to your ebook when you have some time. Now, like I said before, as the note that I sent out on Blackboard, make sure that you take a little bit of time to relax and just to rest. You got a long window to take the exam. And also, like I said before, spend a little bit of time on the new material and then go back and spot check any of the old material that you feel like you need to brush up on. You may be fairly comfortable with everything. Again, the college algebra part was review, and you spent quite a bit of time on the tricks, so that should put you in good stead. And of course, I'll have my office hours today and tomorrow, and I'll send out emails with those. So if you have questions or anything that you about the material or anything, please come by the office hours. But I wish you well with your testing, and also I'm thinking it's going to get warmer, so maybe we lost our winter time for now. But good luck as you test, and I wish you well as you make your transition to the calculus. I think I will be teaching another section of Calculus 2. I do not have a section of Calculus 1. It's a very elegant course. Whatever you do with your Calculus 1, make sure you spend plenty of time and dig below the surface and get all of the theory and all of the symbolic calculation. If it's too easy, then you make it hard. You look for different examples to pursue and you investigate things, because you really have to be quite prepared for Calculus 2. And then Calculus 3 is just a 2 and 3 dimensional version of Calculus 1. So I wish you well as you do that. I think you're going to enjoy the calculus sequence, and you're going to see why you did all of this crazy work in pre-cal. So everybody, thank you for your attendance today. I hope you enjoyed going over a little bit of review. If it were boring, please forgive me. I'm sure a lot of you thought, well, I can do this in my head. And if that's the case, that's really good. So if I see you at office hours, fine. If not, good luck with your testing, and have a very, very safe and restful break. Take care, everybody.
Thank you.
Bye.
You too.
Bye, everyone.
Bye. Thank you.
Thank you. Listen, all I want to hear from you next semester is that you made an A in Calculus 1.
Yes, sir. You got it.
Well, I will keep track of you. So be honest with me. Take care.
Take care.